All right, welcome to a podcast on what's called Hess's Law. And essentially Hess's Law is going to help us calculate heats of reaction, right? Delta H's of the reaction. One key feature of chemical reactions that Hess's Law takes advantage of is that the total energy of our chemical reaction, it doesn't really depend on the path. So if we have a chemical reaction that we could do in one step, or we have a chemical reaction that we could get the same products but do that in 3 or 4 steps, the total amount of energy is the same. The analogy here with these hikers trying to get their way up to the top of this little mountain is that both hikers, if they start at the same point, and one just kind of hikes straight up the mountain, the other one takes a little bit more of a scenic path, they're both going to gain the same altitude, they're both going to have the same potential energy at the end of their trip. Chemical reactions are the same way. The product energy amounts, whether we go from point A to point B, or we go from point A to point C to point F and then back to point B, they're going to calculate out being the same, which is kind of hard to understand right now because you don't have any actual chemical examples. So we'll get to that. But in general, if you want a kind of a formula for how Hess's Law works, if I have a multi-step process that makes up my reaction, I can just add up the delta H of the first step with the second step and however many steps there are. And if I add all those up, that'll be the delta H of the reaction. And sometimes they're positive delta H's and other times they're negative delta H's. But we can use this to help us figure out the overall delta H of a reaction, especially if we have some kind of more complicated or more difficult type of question to answer. Like, for instance, this one here, what would be the delta H for the decomposition of ice? So we don't want to just melt that solid into a liquid, but we also want to see the amount of energy that's going to happen with that liquid being decomposed into gaseous elemental hydrogen and oxygen. So kind of a difficult thing perhaps to throw in a calorimeter and make happen. But what we do know is we have some thermochemical data. We know that if we are going to melt some solid ice into liquid, that it has a heat of fusion of a positive 6.01 kilojoules per mole. We also know that if we have the elements hydrogen and oxygen, right, and they're going to form 1 mole of liquid water, the amount of energy associated with that heat of formation is, it's an exothermic reaction, which is our negative 285.8 kilojoules. So these are kind of 2 related processes to what we're asking here, except it seems like this reaction is written backwards, because we want solid turning into liquid, but then we want that liquid turning into the gaseous elemental hydrogen and oxygen there. So we're close, right? So we can use this information according to Hess's Law. Hess's Law says we can just add up all the different steps and get the total process. We just have to make sure we add them up right. So here's what we can do is we can flip around that reaction, right? As it was written previously, it was backwards with a negative 285.8 kilojoules. If we turn that around and now show the decomposition of liquid water into elemental hydrogen and oxygen, all we have to do is change the sign from negative to positive, right? And it sure looks like this one-step kind of composite situation is now taken care of here by step A, solid to liquid, step B, liquid to gas. So what we can do is we can just add those up. But here's the other thing we have to make sure of, right? We have to make sure that our first step flows into our second step. And when I say it flows into the second step, here's the rule. If needed, multiply the coefficients and delta H by whole numbers to cancel. What you might notice is that as a product of the first reaction, we get the reactant in the second. And these have to match. It has to be 1 mole of this or 1 mole of that. And in this case, they do. So we can just end up canceling those out. But if for some reason, let's say this was 2 moles here instead, right, what we would have to do is we would have to scale up the second reaction so that it uses those 2 moles. So it would be 2 moles there, 2 moles there, and 1 mole here. And that would make this also twice as big. So the energy we'd be dealing with is twice as big. But in this case, that's not what we're dealing with. So let me erase that so it's not confusing. All right. And since our 1 mole of hydrogen, water, liquid as a product, cancels out with the 1 mole of liquid water as a reactant. We cancel those out. And once we have organized our equations so that they're in the right direction, and we've made sure that we have a cancellation of everything to yield our overall reaction, and I want to make sure that that's clear to you, that we start with the reactant, H2O solid, 1 mole of it. Here we have our 1 mole of H2O solid. It makes 1 mole of hydrogen gas, 1 mole of hydrogen gas on the product side of our equation. It also makes 1/2 of a mole of oxygen gas on the product side, and that's what we have here. So we have rearranged these in such a way that they match our composite equation. Now what we have to do is add the delta H's. So we add the 2 reactions to get the composite equation. We add 6.01 and 285.8. And keeping in mind our sig fig rules here, where we can only keep the same number of decimal places in our value with the least decimal places, we throw away that 1/100th of a kilojoule here. We end up with 291.8 kilojoules for this particular process. Let's talk about something related. Molar heats of formation. We've been using a number here already, this negative 285.8 kilojoules. It's the molar heat of formation, just by definition, is the amount of energy involved to generate a mole of a material from its elemental substances. So we have water that's generated from elemental oxygen, elemental hydrogen, and there's whole tables of values of these available to you. There's one in your book that we're going to have to use, and there's a caveat to this. We need to make sure that we know that these values are really only valid at standard conditions. And standard conditions, not the same as standard temperature and pressure. We do have standard pressure still, but now the temperature that we're interested in is 25 degrees Celsius, not 0 degrees Celsius like in gas laws. But these values are valid at these conditions. And the other thing that we need to know is that if we just have elements in their standard states, so oxygen gas or sodium metal, their heat of formation is 0. Right? So that's kind of our starting point for determining all of the other substances. So any element in its standard state, so standard state meaning the state it would be at standard pressure and at 25 degrees Celsius, it has a delta H F naught of 0. The other thing that I should probably point out here is this little naught symbol here. It looks like a degree symbol. That is referring back to the standard conditions. Right? So delta H of formation, standard. All right, so here's how we're going to use this. Right? Another way for us to come up with the delta H of a reaction is if we can reference a table of delta H values, delta HF values for the products in our chemical reaction and the reactants in our chemical reaction. We can just subtract the two to come up with our delta H for the reaction. So for instance, let's look at what is the delta H of reaction for the combustion of methane. Right? So here's our reaction equation for the combustion of methane. We've got methane CH4 plus 2O2 yields CO2 gas plus water liquid. So if you look in your book, I forget the page number, we'll tell you whenever we get to class, but if you look in your book, you can find these values. The heat of formation for methane is negative 74.8 kilojoules. Oxygen gas, that's an element in its standard state, so it's got a 0 there. CO2 gas, negative 393.5. And water liquid is 285.8 kilojoules. Once again, we can see that one quite a bit. The thing I need you to be careful of here is the heats of formation are molar heats of formation. So it's great just to kind of write that in whenever it's 1 mole of something. But now if I have 2 moles of a material, we need to multiply the molar heat of formation by that in order to end up with valid numbers. We kind of started doing that over here, except 2 times 0. Who cares, right? It's still 0. But what we'll see here is that if we were to add up all of the energies, or the heats of formation for our reactants, it gives us negative 74.8. If we add up all the heats of reaction here, or heats of formation for our products, it's negative 965.1 kilojoules. And according to our previous statement, that the heat of reaction is the product's heat of formations minus the reactants heat of formations. So we have our negative 965.1, and then this is negative 74, so that is why we have a positive symbol there now. And if we add those together, we'll see that overall, the delta H of this reaction is negative 890.3 kilojoules. So what is that? Is that endothermic or is that exothermic? Well, you should have expected the combustion of anything to be exothermic, especially the combustion of methane. That's the primary component of natural gas. That's the kind of stuff that you can use on your gas cooking stove, or might be heating up your house right now. It's actually why combustion reactions are so tremendously interesting. This is a very large and negative delta H for that reaction, so we can get a lot of energy out of the combustion of this particular hydrocarbon.